Hi and welcome to a discussion with Ruixiang Tang regarding the science of detecting LLM-generated texts. This is a field that has risen in importance in recent days because of the emergence or prominence of LLMs. We will particularly focus on how you can distinguish text that is generated from an LLM compared to human-generated text. I hope you enjoyed. So I think a good place to start would be talking about what the vulnerabilities are right now. If we're talking about LLM-generated text and how that potentially can be manipulated and what we're trying to avoid with the focus of this paper in particular.
So you mean why we need to detect this LLM text? So you talk about the motivation or...
Exactly, yes. So,
okay.
exactly.
So definitely, I think currently this, I would say this LLM generated text is kind of deep fake. And like previously we know that there like in computer vision domain, people are generate this fake video or images, and it's already got lots of concerns. And recently these larger models just show another vulnerability that actually this generative AI can generate sophisticated text. And for our normal people, it's really hard for us to distinguish them between the human generated contents. So it already causes lots of concerns. For example, I'm an assistant, teaching assistant in Rice University. So I suspect many students actually use GPT-4, for example, for their homework. Like for many coding exam, the student just copy paste the questions into the GPT-4, and GPT-4 can generate the code for them. So it causes a lot of concern in the education system and also in our media, right? So fake news versus AI generated fake news. So it's maybe everywhere in the future. So definitely we need a very reliable system to help us to detect these AI generated contents. So I think it's a very urgent need.
Mm-hmm. In some areas, like you mentioned with education, I think it's critical that you can detect whether or not something's generated by an LLM, but I see potential problems if we're talking about other domains as well. Let's pick the media, for example. Fine, maybe you can detect whether a text comes from an LLM, but how do you know if that's a deep fake result? Like, let's say you have media outlets that are just producing content using LLMs in the first place. How is that a different scenario compared to someone who's trying to generate a deep fake of this? I know that's kind of off topic for the paper itself, but is the question of whether or not it comes from an LLM the critical concern when it comes to, let's say, fake news and this entire space? Do you think?
Yeah, that's a very good question. So I think there's some overlaps between the AI generated contents with, for example, fake news. For example, some news, maybe they are not fake, right? But they are also generated by the LLM. People might use this LLM to polish the news, right? It's also possible. But I think the key idea is that we need to identify whether given news is generated by AI or not. So this is the first step. After this step, we can decide whether this content in this news is correct or not. That's another thing. Maybe we can do the fact checking or something like this. But I mean, for many people, currently we don't know is whether this is generated by AI or not. Because if generated by AI, so people will have more concerns about the contents. Yeah.
Right.
Yeah.
Agreed. So if we're focusing a bit more than on the paper itself, we have two main groups of, let's say, AI or LLM generated text identification categories. So black box and white box. Would you mind giving an overview of what those are and what they mean?
Yeah, sure. So basically, let's start with the black box. So why we divide it into black and white box actually is according to the accessibility to the larger models. So what we call threat model in the security community. So basically, we want to know how many resources we can access to detect this error and generate text. So let's start with the black box setting. So for black box setting is very similar to our researcher, what we call third parties. So basically, we are not the developers of ChatGPT or we are not developers from OpenAI. So in this way, if we want to build a classifier to distinguish these AI generated contents, what we can do is that we just collect many human authored data, right? And we collect also many LLM generated texts. And we can then do some feature selection. So we want to find some features that we can distinguish between the AI and the human, and then we can build a classifier. You can use machine learning or other methods. And then finally, it could be a binary classifier. So given a text, the classification model will tell you whether this comes from human or AI. So that's the high-level idea of the black box detection. So we call it black box because we have no access to the large language models. We can only access from the API level. Like we can call the GPT-4 to collect many AI-generated contents. Yeah.
Right. Okay, so would you mind introducing the white box model as well, and then we can go into more details on the different terms.
Sure. So the white box method is like so we actually have more accessibility. Like actually, we assume that we are the developers of these larger models. So that's I'm a developer of the GPT-4. So what we can do is that we can actually add some, for example, watermarks into the AI generated contents. We can change the model's behavior. And by using this knowledge of watermarks, we can then build some algorithms to detect whether this text contains a watermark or not, and use this to trace the use of these AI generated contents. So this is what we call the white box scenario. Yeah.
Mm-hmm. Okay. If we go back then to the black box model and talk about that in a bit more detail. So we're saying that we want to build some classifier without having access to the model itself. Are you saying we would build one classifier for all kinds of LLMs, or are we talking about building specific classifiers for individual LLMs and having some form of repository of that? Does that matter which approach you would take?
That's a great question. So I would say people try both. Like, but ideally, definitely we want to build a model that we can identify all the larger models. But in practical, I think it's infeasible, because for different larger models, they have different maybe training data, different training strategies, so their behavior is different. So it's really hard for us now to find some universal features that we can distinguish between LLM-generated text versus the human authored text. So what people currently do is that they will build a model for one specific large language models. But definitely we will try this model's generalization ability to other large language models. But according to current research results, the generalization ability is very poor. So this is the key problems for the black box model, because this black box model we actually learn this feature from the training data. But for our human, we can only collect limited data sets, right? We can only, for example, you can collect many human authored data and many LLM-generated data, but still it's limited. And then this limited data maybe contains some bias. This depends on how you collect the data. So maybe the model just learns this bias. So this is why this classification model is hard to generalize to some, for example, new, maybe, what is the out of distribution data, like new larger models. Yeah.
Yes. So I'm bringing up a figure on the screen here. That distinguishes the white box from the black box, and I would just like to focus a bit more on the pipeline, let's say, that is associated with the black box detection. So we mentioned data collection, also feature selection, and the classifier. Could we go into those in a bit more detail? So if we start with the data collection, like what kind of approaches would you take in the data collection step?
Yeah, that's a great idea. So from this figure, so firstly, I would say this figure is not, so some people will think, okay, this perfectly from the left to the right. We first do the white box and then do the black box. So that's not the idea for this figure. So basically we provide two approaches. They are parallel. Yeah. So for the black box detection, so yeah, like you said, in the first step, we will collect the data from both human and the larger models. So for the human, I think definitely a very easy way is that we just maybe hire some volunteers to collect their data. But the problem is that it's time consuming and maybe it's also very costly. So what people usually currently do is that we just collect the data from the existing source, like from the Wikipedia, from the book, or from the like some blogs or this media like Twitter, or yeah, so many of these existing media source to collect the human data. And for the large language models, there are already many data sets you can use them. So many people already collect many large language models outputs. But here the problem is that we need to define a domain, right? For example, you want to you want to collect the news from humans and also from AIs. So you need to define a domain. So otherwise, you just collect too many sources and you don't know where they come from. So that's a problem. So you need to define a domain and also define the scales, and you can find this resource from both the human and the large models. Yeah.
Mm-hmm. If you're also acquiring data from, let's say, Wikipedia pages, then you kind of run into a circular argument, I guess. Like right now, I guess we're fine, but in a few years, if we have LLMs really producing a lot of text, you wouldn't necessarily know whether the text there, unless it has a watermark of some sort, whether it's generated by an AI to begin with. So there could also be, I guess, some sampling issues there.
Definitely. Yeah, so that's correct. So I mean, this is a problem. So in the future, I mean, even from the internet, it's really hard for us to tell where this data is from LLM or not. But what we can do is that because LLM just appeared like 2 years, maybe 1 year ago, you can approximate this timeline and select this data. They are very likely to from human. But in the future, I agree with you. Even for Wikipedia, it's really hard to tell whether this come from AI or human. Yeah.
Mm-hmm. Okay, so we get some data, and how would you go about segmenting that? So you want it to be specific to the kinds of applications you're considering. Let's say it could be news data, or what would be good? Like, do you have an idea of what good parameters for dissecting that data is? Like, what is it that you would use for grouping if you want something very in sample? Are there things that you could group on that are more appropriate than others? If that question is clear.
Yeah, so you mean how to group the data for...
Like, what parameters do you consider mainly? Let's say you want to identify some arbitrary text that you found, whether or not it's LLM generated or not, and you want it to be as versatile as possible. So you want to cover, let's say, a large scope. What are the features that you would... Yeah, like, what are the important parts to distinguish between when we're saying... Because we're saying that the LLM or that the classifier would not be applicable across the entire domain.
Yeah,
and
definitely.
What is it, if there are any key variables that prevents it from being applicable across the entire domain? That's what I'm trying to get to.
Yeah, because entire domain, you mean the endless domain, right? So it's
exactly.
impossible for us to collect that much data. But currently, people just, I would say, in academia, people just focus on some key domain, like the question answering, storytelling, news generation, something like this. So it's very, this is from the research purpose. We can build some benchmark data sets to evaluate the model's performance. But if we really want to use it in the real world, definitely we need to collect more domains, like you said. Yeah, if you want to make this model generate to more domains. Yeah.
Mm-hmm. Okay.
And you can go ahead.
Yeah. So how about we move over to the feature selection? Was what I was going to ask. Like what we do in that step, and how that fits into the larger picture.
So for the feature selection, that means if we collect many data, right? So then the next step is that what kind of feature we can use to actually to help the model to identify these key features that we can distinguish them. So here we talk about maybe 3 of them. So firstly, we can find some statistical disparities between the AI-generated contents and the machine-generated contents. And we can also find some linguistic patterns. And we can also do the fact checking or fact verification. Yeah, these are the 3 points I talked about in this paper. Yeah.
Mm-hmm. Would you mind elaborating a little bit on what each of those entail?
Yeah, sure. So for the statistical disparities, basically we want to identify these patterns in the AI-generated contents. For example, if you just calculate the token, like the frequency of the tokens, you can find some patterns. For example, the GPT-4, they are prefer to use some words than others. Actually, there's one research paper currently, they show that for some verbs or longs that usually used by larger models. They are, so recent papers, if you extract their abstracts, many people use this larger model to generate this abstract for their research papers, and the frequency of this word is increased recently. So basically, you can find these patterns in these AI-generated contents. Like if you play with GPT-4, you can find then they have some preference to use some certain words. So that's a very simple examples. Yeah, for the linguistic patterns, that's more like for example, example is that for the larger models, they might tend to use a neutral sentiment. But for our human, we have lots of different sentiment like humor or hate or something. So for our human, we have diverse this kind of sentiment. But for the larger models, they tend to use a neutral sentiment. So these are linguistic patterns, and also for the fact verification. So this is because for the larger models, they usually will have these hallucination problems, which means that they will just randomly generate some facts or something. So if you can detect them, there also be a very useful features. Yeah.
Do you have a view on which of these are more robust now? Like, just listening to you talk about this off the top of my head, I would say that statistical disparities seems the least robust. No, like it seems like something that if you have an update to the model, that would very easily not be the case anymore. That those particular words would reappear. Maybe I'm wrong about that. Do you know what the models in the space, if there are any yet, like classifiers, what they use mostly and which ones are most robust?
That's a great question. So currently, I mean, if you just based on one of them, then you cannot get a very good performance. I would say none of them is very robust because this is because for larger models, you can just use a simple prompt, like you can change their behavior significantly, right? Mm-hmm. Because even for the sentiment, you can add a prompt like, please reply, or please provide an answer in a humor sentiment. Then you can significantly change the output. So I would say London is very robust now. So what people do now is that you can try to find as much as possible and integrate all of them into the classification. And also for different domains, I would say the importance of different features is also different, right? For example, for news, maybe the fact verification is more important, but for the storytelling or maybe the linguistic patterns is more important. So it's also task specific.
Mm-hmm. Are there at the moment right now any black box detection models that are out there that you can use that you can sort of do benchmark tests on to see how well they generalize on different kinds of text that you feed them? Or is this space so new that you really don't have anything to test on?
Yeah, there are many benchmark data sets. Recently, if you search on these kind of papers like benchmarking, detecting larger models, most of them actually they are in a black box settings, and I would say currently there is no reliable black box detection method because so I would say not reliable because if you want them to really use in the real world, I would say there is no system, and also another consideration is that people might mix of them, like. Some sentences is generated or polished by the larger models, but others not. So it's also concerns. There's some concerns about the detection resolution. So how about the resolution of your detecting system? So that's my answer for your question.
Mm-hmm. Okay, I want to touch upon the classifiers as well, but since we're already talking a little bit about the shortcomings, maybe of the black box model, is there anything else you think is relevant to mention there? So we mentioned robustness. We mentioned whether or not you dilute the text with other sentiments. We mentioned if the text is very short. Is there anything else? Like, are there any other critical shortcomings of the black box detection model or approach that you think are worth highlighting?
Yeah, I think the problem of the black box is that this is a data-driven method because all these features and all these they actually learn from the data. So the data is the most important thing for the black box detection method. So, I mean, if you cannot guarantee a very high quality of the data, then the model will have many problems. Like we have this shortcut learning problems that this classification model, maybe they are lazy. They just want to find the easiest pattern in the data to distinguish them, right? And maybe then it will cause this generalization of problems. So I think that's the key limitation or drawback of the black box, because it's a data-driven problem. So if the data quality is not that good or the data diversity is not that good, so then your model will have lots of problems. Yeah.
Before moving over to the white box detection, I would just ask if there are any, let's say, distinguishing qualities of the kind of classifiers that you would use in a black box detection approach compared to other classifiers. So if we just compare, because you could build a classifier in many ways, but is there anything that distinguishes the approaches you want to take in a black box detection scheme from the status quo?
So you mean the evaluation metrics or something like this, right?
So something of that sort. Anything in general, like what kind of approach you use for actually building the classifier, or evaluation metrics, anything like that. Anything that just differs from status quo.
Yeah. So how to build this classifier actually is a very standard machine learning pipeline. You collect the data, you find the features, and you then have the model just train these models and use the validation data set to choose the best model you have, and then you can test your data on a testing data set. So currently we can use so basically it's a classification model, right? Classification task. So we can use like the AUC, ROC, this kind of metrics to evaluate the model's performance. But I think there's a unique point that because this is I would say this is more like a security problem. So we actually care more about the model's true positive rate under a very low false positive rate, which means that we actually, if we set the false positive rate to 0.1%, and in this case, we want to know what's the true positive rate. So basically, we actually change the threshold of the decision making. Yeah. So this is very important. So we can consider two classification model, right? For example, one classification model can get an AUC around 50.5%. So basically it's a random guessing, right? And another model, this model can reliably to detect 1% of the AI-driven contents. And for others, they are randomly choosing. So for these two models, it seems that if you use the AUC metrics, they are very similar performance. But definitely for the first one is useless. But for the second one, they are practical because you can use this model to identify some text with very high confidence. Even they can only classify like 1% of them. So this is why we mentioned that we need to evaluate these models not only from this AUC, RC from average perspective, but also need to consider at a very low false positive rate scenario. Yeah.
I think you mentioned in the paper also the model's confidence in its classification, whether or not you can generate metrics as an output that give you that kind of information. Could you maybe shed some light on where we stand there? Is that something that's easy to do with these models, or are there significant challenges?
Yeah. So if you use, for example, deep learning models, and then these models are actually, they are inherently can provide you a probability, like the confidence score. If you use, for example, the softmax as the final output probability. So for example, the model can tell you, the model classify this text as AI-driven contents with 80% probabilities. And actually in many scenarios, people need this, we call the confidence score. We want to know how confident is the system to detect it. But the problem is that, if you directly use these kind of probabilities, they have many problems. And, so for example, the model maybe become overconfident. The model always assign a very high probability for their prediction. It's possible. Actually, people find this especially for the deep learning models. So this is why we need a technique called it's called uncertainty calibration. So we want to calibrate this confidence score or probability, which means that if the model's confidence score is 10%, which means that only 10% of the samples are correctly classified. If the model provides a confidence score of 90%, which means that 90% cases the model did correct classification. So this is why we need to provide not only to provide a confidence score, but we also need to calibrate it. Yeah.
Okay, understood. Good, but then let's move over to the white box detection approach as well. We also have it on the screen. So if you would like to just summarize maybe what the difference is now that we talked in black box in detail, the difference in what we can do when we actually have access to the model.
Yeah, sure. So different from the black box detection method. So now for the white box detection model, you can assume that you are the developers of the GPT-4. So then you have more access to the models and you can change the model's decisions over the output behaviors. So I would say a very natural way to do this kind of white box detection is that we can add some watermarks into the AI-generated contents, right? So here we actually have two methods. One is the inference time watermark, and another one is the post hoc watermarks. Maybe post hoc watermark is more easy to understand that. So after the AI-generated contents, we can add some watermarks into the text. For example, we can change some words to a specific word. We know this changing rule, and then after we gave this output to the users, we can use these rules to detect these AI-generated contents. So that's for the post hoc watermarks, which means that we didn't touch the generation process of this text. We just, after we get the text, we add some watermarks into the contents. And there are many traditional algorithms to do this kind of watermarks. But for the larger models, I think there's a unique opportunities that it's the inference time watermark. So why we can do the inference time watermark is that if you look at how this larger model actually works, so given some prefix, the larger model just generate the next token and then next token step by step. But the key problem is that how do we actually choose the next token, right? Yeah, maybe you can go to the...
I think there's a figure on that down here as well,
this
right?
figure,
this
figure 4, yeah. Like here, there's a prefix like I saw cat on a, and then we need to choose the next token. But which token to choose? This is a very interesting point that we can add some watermarks. So previously, people just use some random algorithm like from the top 10 or top 100, we just choose one of them as the next token. But how about we have a hashing algorithm, right? We have a secret hashing algorithm to decide which token to choose. And this process actually depends on the previous token, like the Actually, we according to the token we have a hashing function and to choose which token to choose in the next step. Yeah. So in this way, we can also add watermarks in this generation process and use it to detect the AI-generated contents. Yeah. And I would say this is more promising now. Yeah.
Right. And so the hash function would map from a word, I suppose, or a letter onto what would it map onto? Let's say the top 100 words in that we could potentially pick for the next token, or what is it that we would actually map?
Yeah, there are actually many different choices, and actually in this in the figure in this example, it's very famous paper. It's a SML best paper. So what they did is that according to the previous token, we can have a hashing function, and we can divide the whole vocabulary into two equal parts. For example, one part is for we call the red list, and another part we call the green list. And we only choose the tokens from the green list. So then in this way we can add watermark. So ideally all the text should choose from the green list. And how to detect it? So given a text, right, we can, according to the previous token, we can calculate what's the red list and what's the green list for the next token, and to see whether the next token actually is chosen from the green list. So for each token, we need to do this kind of verification. Yeah.
Okay. And so I guess also with this approach, similar to what we said about the black box categorization, you would be, well, your confidence would increase the longer your text is. No, because I guess this is a probabilistic assignment. So also here, I guess you would be somewhat vulnerable to very short sentences if you want to.
Very short, yeah. But I agree with you. But a good property for this watermarks that considering a complex scenario is that there's a mix of AI-driven contents and the human authored data. Actually, with the watermark method, we can somehow to find the change point, right? Like the before this point, they are like almost half red word and half green word, which means that is maybe generated from human. And after certain points, all the words comes from the green list. It's very likely that from this point, then it's generated by the AI. So I would say for this watermark method, they might provide a high resolution for the detection system.
Mm-hmm. And even, so correct me if I'm wrong here, but even with a text where you intermingle very frequently AI-generated text or LLM-generated text with, let's say, text that you've written yourself, if you consider that text as a whole, you would still be able to statistically say that this probably comes from, at least part of this probably comes from an LLM.
Yeah. That's correct.
Okay, so that, okay. Okay, cool.
But you are right. If the text is very short, it's still really hard to detect it. That's a problem. And another problem for this watermarking method is that we need to change the selection process, right? So actually, it has an assumption that for the next token we have lots of choice, and we can choose one of them as the next word. It may be feasible for many cases, but for some certain cases, like the code generation, it has less flexibility, right? For the next, because if you want the code can be runnable, definitely there for many tokens you have very less choice, or even you only have one choice. So in this way, how to add this watermark for the code generation? That's a very interesting problem.
Mm-hmm. Are there any other approaches that you could take besides using some form of hash function for this? Like, are there any other inference time watermarking techniques that differ fundamentally from what we discussed now?
Yeah, definitely. If you don't use this hashing function, definitely you just add some, I would say, prior knowledge into the generation process. So you can change the words, like the distribution or something. And all these methods you just have a rule or algorithms to change the model's decision, which token to choose in the next step, and then you can use this to detect it. I mean, there are series of works, but they both follow this assumption. Yeah.
Right, but are there any such approaches where the problem of code generation could be circumvented? Like, it doesn't seem to. So if we're just saying, like, if we're saying that they all fundamentally rely on a rule for changing the next token, which it somehow needs to be, it seems to me like the problem of code generation is still a big problem, no? If you want to verify it. Do you know of any approaches that are in the category of inference time watermarking that can be successfully used with, let's say, code generation?
Yeah, for the code generation, maybe we just have a high level watermark. So currently this watermark is like a token level watermark, right? Which token to choose. But we have a higher level watermark is that semantic level watermark. For example, we can, if the code we have the syntactic tree of the program, right? Maybe we can add some patterns in this syntactic tree. When we run the models, we can find, when we run the code, we can find some patterns. So that's maybe a possible way. Also for the text, maybe we can just change some syntactic of the generated text, like the syntactic structure with text or something, and use it to detect the AI generated contents. It's not just from the token level, but maybe a higher level. Yeah.
I'm not super familiar with how LLMs generate code, but do they always generate them together with a syntactic tree, or is that not generally the case? Because if you have one, then yes, you could encode it, but then normally, well, do you normally get something like that if you generate it with an LLM? Is there some
No,
intermediate representation?
LLM
No?
just generate the code for you. But when you
Yeah.
run the code, you can get a syntactic tree, right? So we can use that. Maybe you can just, when you train the model, you can ask them, or you can design some specific patterns in their syntactic tree. And then maybe you can, all the generated code, if you run them and get their syntactic tree, they have a certain patterns, and you can use this pattern to detect it.
Okay, so you're envisioning more like a two-step process then. You would generate the code, and then the watermark encoding would be like a second step where you have your entire code, you would generate the tree, and then in that tree you would do the encoding. So you would do it in two steps then, essentially.
Yeah, 2 steps. But if you just from the code, maybe it's really hard for you to get some watermarks. Yeah, to get some watermarks information. Yeah.
Are there any other challenging domains where where inference time watermarking might not be successful?
Yeah, I mean, maybe for this, I think there are several points. One is the length limitation, like you said. If the text is too short, there's problem. Second is the for this code generation, if the next token there has very I would say the entropy is very very low, which means that you have a few choices. Maybe then this inference time watermark is not that useful. And maybe the third circumstance is about the open source model, right? Maybe it's not just for the inference time watermark, but it's for the white box watermark. So because for this white box detection method, we assume that there is one-to-many relationship. There's a big company like OpenAI and many people use their tools. But how about open source scenario? Like Meta, they just open source Llama 3, or maybe in the future Llama 5 or Llama 10. Maybe these models are powerful as the GPT-4 in the future. And everyone, they just use this open source model, and they have the fully control of the model. They can fine tune this model and change their sampling strategy to how to generate the next token. So in this way, you cannot force all these companies to add these watermarks in their models, and especially for this open source model, right? So that's a problem. Yeah. In the open source challenges, I would say there is currently no solution for it. And actually, I'm worried about it because I would say in the next 5 years, there definitely some very powerful open source model, and everyone can access it and fine tune it and use it for maybe some malicious purpose. How to detect it, that will be a very challenging problem. Yeah.
Mm-hmm. Are there any ideas for how you could detect that using an open source model?
Yeah. So firstly, if we think about the black box detection method, definitely we cannot build a very generalized black box detection model, because the user, they can fine tune this model to significantly change the behavior. And for the white box detection method, like maybe you can add some watermarks into the model generated contents before you open source them, like the high level, maybe semantic level watermarks. But still, the problem is that if the user has the fully control of the model, and they can fine tune the model and change their behavior, how to build a robust watermarks even under the fine tuning process, that's a very challenging task. And I didn't see too many papers about it. Maybe it's too challenging.
Mm-hmm. What's the idea for the ones that are not open source? So we have a watermark in place. How would the verification procedure work for that? So let's say you're working for a university and someone sends you a text. What would be, let's say, the step-by-step process for verifying whether or not that now contains a watermark?
Yeah, I would say, suppose, for example, if I'm a company, I can provide a detection API to the university, right? So university just upload their text to my API, and then we can use this watermark detection algorithm to detect whether this text actually contains our designed watermarks. And I can provide actually a probability or even p-value for you, how confident that this text actually contains a watermark. Yeah, I think that's the case how we can provide such detection service. But the problem is that who can access this detection API, right? Maybe university, they can access. How about others? Because if the adversarial attackers, they can also access to this API. Maybe they will use this API to maybe bypass the watermark detection algorithms, right? They can change a little bit about text and see whether the detection API can still detect it. And iteratively, maybe they can find a way to bypass existing watermark detection method, or find a way how to remove the watermarks from the text. That's possible. So even we have a watermark algorithm, then we still to consider who can access to the API, who can access this detection ability, and also consider the potential adversarial attacks. Yeah.
Mm. Do you see any opportunities for making something like that public? Like, I'm thinking of this from the perspective of, like, let's say you wanted to have verification of news. Let's use that as an example. And you have millions of people, billions of people watching news, and they want to be able to verify whether or not this is actually from a credible source or not. Do you see any possibilities to, in the event that we don't have open source models, but we really have models provided by large organizations, that those, like, that you could provide something widespread, a widespread verification API, for example, without having significant breach risks for that?
Yeah, I think the risk is that if everyone can access to the API, definitely people will come up some algorithms, attack algorithms that they can fool the system, definitely, right? Because for this for existing detection, these watermarks, I would say they assume that the attacker has no knowledge about the watermarking algorithms. If the attacker has the knowledge about the watermarking algorithm, definitely they can design adaptive attacks that change some words or replace some words, and then they can fool the system. So that's the concern. If everyone can access, definitely people will also attack this system. There's a endless game between attack and defend. Yeah.
Can you maybe, for the last few minutes, also give a short overview of what kind of paraphrasing attacks are out there? First of all, like what we can play around with in terms of like altering the text, and what approaches are most effective right now?
Yeah, so actually you can use very simple way to attack existing like this watermark system, that you just change the words. You can ask another larger models, like I can ask a Llama, like Llama 3, please help me to refine or polish this text. And because for this open source model, they do not have any watermarks in their sampling process, you can fully control it. Then the generated text is very likely they will maybe remove many watermark tokens. Yeah, so in this way, they can significantly reduce the detection accuracy. So you can check many recent papers. I would say if you can change like 50% of the words or tokens, it's very likely that the detection accuracy will drop below to, let's say, 70%. Because for each, actually, this is also good properties for these watermark algorithms. You can actually, for many methods, you can have a mathematical provements or theory to know that the robustness of these watermarks. Like if we change 20 words of the watermark text, how likely that we can detect it, or how it will change our confidence score. You can predict it. But definitely if you change too many words, no watermark algorithms can guarantee that you can still detect it. Yeah.
Mm-hmm. Okay, if we zoom out again and look at this now on a wider societal scale again, what do you think are our best bets for ensuring that we're prepared when these models get rolled out? Like, not necessarily from the perspective of being able to identify whether the text is generated by LLMs, but if we're not able to do that, do you see any other ways to get around the bad consequences that could arise as a result?
Yeah, that's a great question. Actually, I'm worried about this, and I do not think we are prepared for it. Like, there are already many bad cases, like people in the darknet, people use this larger model, fine-tune on this, for example, malicious data, and they can create larger models for malicious purpose, like the malware code generation, phishing email generation, there's already many in this larger model for this misuse. but we cannot control it. This is because when we public or open source this model, we do not have a very strict regulation, but it's controversial, right? Whether we need to have a restriction or this kind of for this. But definitely in the future, I believe this problem is we cannot just solve it from our computer science community. Definitely, it also need to integrate, for example, the government, the policy makers, how to have a more comprehensive regulation framework. So who can access to this powerful model and what we can do for these powerful models. Like if everyone can fine tune these models, definitely people will use these models for the malicious purpose. Yeah.
Mm-hmm.
So I think it's not, it's not just a problem that we can solve from the computer science community. Yeah.
Right. Agreed. In terms of upcoming research, though, or future research that you think the community should focus on, given what you know about these detection systems, what is it that you would advocate needs more focus here? Like, are there any avenues that you think are promising? Like a lot of the stuff we touched on, we sort of said that there are big gaps in all of these approaches, but are there any areas where you feel it's promising to like really put a lot of effort into future research?
Yeah. So for me, I think I will focus both on the white box detection and the black box detection, and I want to solve the limitation for both methods. Like for the black box method, definitely I want to improve the detection generation ability, right? So this is a very challenging problem. So if we can have some improvement on this part, then definitely this black box detection model has actually have many advantages. So that's for the black box. And for the white box detection method, I will try to solve the problems is that how can we find a sweet point for the watermark strength and text quality. So currently, if you add very strong watermarks into the generated text, it will also impact the text quality. So how to find a better algorithm that we can somehow find a good trade-off between the watermark strength and the text quality, that's a very interesting research problems. Yeah. Mm-hmm. But my conclusion is that currently there's no reliable detection system for use. Yeah.
Right. Yeah. Before closing, I would just like to ask if there are any other parts of the paper where you would like to conclude that we perhaps didn't touch upon. If there's anything else you would like to say just before we wrap up the discussion.
Yeah, I think maybe we covered most part of the paper. Yeah. Maybe one part you can add is that one problem for the black box method, another problem with the black box method is that every month we have a new model, right? So how to make sure that we can build a benchmark to evaluate these larger models, to evaluate this black box detection on these new models. That's a very challenging and I would say time-consuming task. Yeah. So who will build this benchmark to for example, there is a platform that you can upload your classifiers and you can know your detection accuracy with all existing larger models. That would be perfect. But then currently we do not have such benchmark data sets. So if in the future we can build such benchmarking data sets, that would be very helpful for the whole community. Yeah.
What do you think would be required to build something like that?
So like first we need to include as much as larger models as possible, right? We want to include these larger models from different sources and also from different architectures. So we have the transformer, and then now we have many other architectures like Mamba or other this kind of architectures, right? So this first one, and the second one is the domain. Like I said, so how about the text domain, like the news, storytelling, question answering, we want to include as much as possible. And also considering different lengths, like short text, long text, and also need to consider maybe the variance of the larger model outputs. Like we might to change the prompt, how we guide the model to generate the text and to see the different the output under different prompt settings. Yeah.
Have you seen any initiatives going in that direction, even if we don't have something like that at the moment?
Yeah, there are some papers. There's some public available papers now. I think, yeah, for the benchmarking, how to build such a data set to evaluate the black box detection method. There are some papers. Maybe I can send you later in the email.
Sure. Yeah, then we'll include that in the description for people that are interested as well.
Yeah.
Good. But I think then we can end the discussion here. I appreciate really you taking the time to go over the paper with me. I had a blast going over it, so thank you for doing that.
Yeah, thank you for having me.